Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will carry us across the dark oceans of the universe, following ancient beams of light that have wandered through space for billions of years before finally arriving here, gently touching your eyes, your screen, your little corner of the night. Before you settle in and get comfortable, I'd love if you could take a moment to like this video and subscribe. Only if these quiet explorations bring you some peace. And if you feel like it, leave a comment letting me know where in the world you're listening from and what time it is there right now. It's always strangely comforting to see how many distant lives gather together beneath the same sky. Each of us awake in our own small pocket of time. Now, you can dim the lights a little more, maybe let the soft sound of a fan hum quietly in the background, and together, let's drift into one of the strangest stories modern physics has ever uncovered. Tonight, we are following light itself, not just light from lamps, or candles, or the morning sun spilling quietly through your window, but ancient light. Light born before Earth even existed. Light released from galaxies so distant that their glow began its journey long before mountains formed, before trees covered the land, before any creature on this planet had ever opened an eye to the stars. And somehow, impossibly, those photons are still travelling. Even stranger, according to relativity, they may never have experienced time at all. At first, that sounds almost poetic, like something written in an old science fiction novel, or whispered in the final pages of a philosophy book read too late at night. But hidden inside modern physics is a deeply unsettling idea. For objects moving slower than light, time stretches and bends. The faster something moves, the slower its clock appears to run. Astronauts aboard orbiting spacecraft age ever so slightly less than people standing on Earth. Tiny particles created high in Earth's atmosphere survive longer than they should because they're moving so quickly through space, and as motion approaches the speed of light itself, that stretching becomes more and more extreme. Imagine an old clock hanging quietly in a train station. Now imagine that clock slowing, more and more, until its hands barely move at all. That is roughly what relativity predicts for something moving incredibly close to light speed. And light itself moves at that ultimate limit, which leads to a strange and delicate conclusion. If you follow the mathematics all the way to that edge, the passage of time along light's journey appears to collapse towards stillness. A photon released from a distant galaxy may cross nearly the entire observable universe, and yet the amount of time experienced along its path approaches nothing at all. From our perspective, that journey may take 13 billion years, but along the path of the light itself, there is no drifting afternoon, no ancient waiting, no slow passage from youth into age, no ticking clock hidden inside the photon. The light leaves, the light arrives, and between those two moments, the universe experiences billions upon billions of years. It is one of the most beautiful paradoxes in physics. Tonight we're going to sit quietly inside that paradox for a while, because something even stranger begins to emerge once we look closer. These timeless photons somehow still change as they travel across the expanding universe. Their wavelengths slowly stretch, their energy softens, their colour drifts gently toward red. Ancient visible light becomes infrared, then microwave radiation, and someday, in the unimaginably distant future, perhaps long radio waves so stretched and faint that they can barely be distinguished from silence itself. The photon never feels old, and yet it arrives aged by the cosmos around it. It is almost as though the universe itself is changing the meaning of the light while the light remains internally untouched. Like a letter carried across centuries, still physically intact, but arriving in a world so transformed that its original language has nearly been forgotten, or like hearing a familiar song played slower and slower over time, until eventually the melody becomes long, deep, and almost unrecognizable. This slow stretching of light is called redshift, and hidden inside it is one of humanity's greatest discoveries. Redshift revealed that the universe is expanding. It showed us that distant galaxies are drifting away from one another as space itself quietly grows. It allowed astronomers to measure the history of cosmic expansion, to peer backward through time, and to glimpse some of the earliest structures ever formed after the birth of the cosmos. But redshift also carries something softer, and perhaps a little sadder. It tells us that the universe does not simply contain history. It slowly pulls history apart. Every beam of ancient light travelling through space is stretched by the growth of the cosmos itself. The farther the light travels, the more the universe expands beneath it, like a road lengthening under the wheels of a moving car. And so the oldest light in existence reaches us weakened, cooled, and reddened. Not because the photons grew tired internally, but because the universe changed around them during the journey. That distinction, small and subtle as it may seem, changes everything. Because tonight's story is not really about light alone. It is about time, about memory, about distance so enormous that even light struggles to carry the past intact across it, and perhaps most quietly of all. It is about the strange realization that we may live in one of the very few eras in cosmic history when the universe can still be clearly seen at all. Far in the future, galaxies beyond our local cosmic neighborhood may slip so far away that their light can never reach future observers. The oldest radiation in the universe will stretch thinner and colder until it fades into near undetectable stillness. The evidence of the Big Bang itself may someday disappear beyond observation. Future civilizations, if any still exist, might look upward into the dark and never know the true story of the cosmos. But for now, the ancient photons are still arriving, still carrying whispers from a younger universe, still crossing the darkness toward us. And so, before we drift deeper into expanding space and fading starlight, we should pause for a moment beside one simple and astonishing question. How can something timeless still grow old? If you were to send a message across the ocean hundreds of years ago, you might place ink onto paper by candlelight, seal the letter carefully, and hand it to a ship disappearing slowly into the fog. Storms might rise and fall during the crossing. Kingdoms could collapse. Entire generations might live and die before the message finally reached another shore. And yet the letter itself, tucked quietly inside its wooden chest, would experience none of it. In some ways, a photon is a little like that, a silent messenger crossing impossible distances without carrying any internal sense of the passing years. Modern physics tells us that light travels at the fastest speed the universe allows. Nothing with mass can quite reach it. No matter how powerful an engine becomes, no matter how long acceleration continues, the final boundary always remains just ahead. Light occupies that boundary completely. It does not approach the cosmic speed limit. It is the speed limit. And because of this, ordinary ideas about time begin to soften and blur. For most things in the universe, time behaves normally enough. Your body changes. Coffee cools on a table. Rain falls. Trees grow quietly beneath the seasons. Every physical process carries its own little rhythm forward. Even deep in space, stars slowly burn through their fuel over millions or billions of years. But as motion increases, relativity gently reshapes those rhythms. You can imagine time almost like a flowing river. For objects sitting still, the river moves normally. But for objects moving faster and faster through space, more and more of their motion is redirected away from time itself and into movement across distance. Their internal clocks slow, their chemical reactions slow, their aging slows. Not enough for you to notice while driving down a highway, of course. Even aircraft pilots only gain tiny fractions of a second over a lifetime due to relativistic effects. But the universe becomes very different near the speed of light. At speeds unimaginably close to light, time nearly freezes. And for light itself, the mathematics reaches a strange edge where the ordinary idea of a ticking clock no longer applies at all. Now, there is an important subtlety here. One physicists are always careful about. Strictly speaking, relativity does not allow a proper frame of reference for light itself. You cannot ride alongside a photon and look outward from its perspective the way you could sit inside a moving train. The equations begin to break apart at exactly the speed of light. But if we move gently toward that limit, if we imagine clocks slowing more and more as motion approaches light speed, we begin to glimpse why physicists sometimes describe light as timeless. For the photon, there is no long voyage through darkness, no sensation of crossing billions of light years, no awareness of stars forming and dying while it travels. The photon leaves a galaxy, and then it arrives. That is all. Meanwhile, outside the journey, the universe transforms completely. Entire galaxies collide and merge. Black holes slowly feed and grow. Stars bloom and disappear like sparks in a fireplace. Worlds form from dust. Oceans rise and vanish. Species appear, linger briefly, and fade. All while ancient photons continue moving silently through the expanding dark. This creates one of the deepest emotional tensions in cosmology. The photon itself does not internally age, and yet something about it undeniably changes. When astronomers observe ancient light, they find that its wavelength has stretched. Its energy has softened. Bright blue or visible radiation from the early universe may arrive billions of years later as infrared light, or microwaves, or even longer and colder forms of radiation. The universe seems to gently pull the light apart during the journey, and this raises a haunting question. How can something without an internal clock lose energy over time? Normally, when we think about change, we imagine a process unfolding gradually. A candle burns lower, a battery drains, a person grows older. All of these require time passing inside the system itself. But a photon does not carry an internal before and after in the ordinary sense. So where does the change come from? The answer begins to emerge only when we stop focusing entirely on the photon and begin looking more carefully at the universe surrounding it. Because the cosmos is not static. Space itself changes while the photon travels, and that distinction matters enormously. Imagine walking across one of those long-moving walkways in an airport late at night. If the walkway beneath you suddenly stretched longer while you moved, your journey would quietly change even if your own pace remained identical. Or imagine drawing waves across a rubber sheet with a marker. If the sheet slowly stretches while the waves travel across it, the spacing between the waves widens too. The wave itself did not decide to slow down. The surface beneath it changed shape. In many ways, this is closer to what happens to light in the expanding universe. The photon continues moving exactly as light always does, but space-time itself slowly expands beneath the journey, and because light behaves like a wave as well as a particle, the stretching of space stretches the wave along with it. The farther the photon travels, the more expansion accumulates beneath its path, and the longer its wavelength becomes. This is why the oldest light in the universe arrives cold and reddened, not because the photon internally decayed, but because the geometry of the universe evolved around it. And perhaps this is what makes Redshift feel strangely emotional when you sit quietly with it long enough. The photon carries a memory from the distant past, but the universe refuses to hold still while that memory travels. By the time the message arrives, the cosmos that emitted it is already ancient history. Even the light itself has been transformed by the distance between then and now. Like hearing the voice of someone from childhood through an old recording stretched and softened with age. The information remains real, but time has gently altered the way it reaches you, and as we continue drifting deeper into this expanding universe, another realization slowly begins to appear through the darkness. Perhaps light is not merely revealing the cosmos. Perhaps light is quietly revealing the shape of time itself. Long before telescopes could peer into distant galaxies, before satellites drifted silently above Earth, before humanity understood even the existence of atoms, light already felt mysterious. It illuminated the world so effortlessly that people rarely stopped to ask what it actually was. You wake in the morning and sunlight pours quietly across the floor. A candle flickers against a wall during a power outage. Lightning briefly turns the night sky silver. None of these experiences feel strange at first. Light simply appears, instantly and naturally, as though brightness itself were one of the permanent ingredients of reality. But the deeper scientists looked into light, the stranger it became. At first, many believed light behaved purely as a wave. That made sense. Waves spread outward, they overlap, they bend around corners, they create interference patterns like ripples crossing on the surface of a pond. And light does all of those things. If two beams of light cross paths under the right conditions, they can strengthen one another in some places and cancel one another in others, creating delicate bands of brightness and shadow. It resembles the quiet geometry formed when rain falls into still water. For a while, the wave explanation seemed complete, but then came a series of experiments that cracked the picture open. Scientists discovered that light also behaved as though it arrived in tiny packets, little concentrated bursts of energy. When light strikes metal, for example, electrons can be knocked free from the surface. Strangely, dim blue light could trigger this effect, while extremely bright red light sometimes could not. It was not simply brightness that mattered, but the energy carried by each individual unit of light. Albert Einstein helped explain this mystery by proposing that light sometimes behaves like tiny particles, later called photons. And suddenly, light became two things at once, a wave and a particle, not switching back and forth like an actor changing costumes, but somehow carrying both behaviours together in a way that still unsettles physicists more than a century later. Even today, quantum mechanics works with astonishing precision while remaining deeply resistant to ordinary intuition. It predicts reality beautifully, but explains it in ways that often feel slippery and dreamlike, and nowhere is that dreamlike quality more visible than in the famous double slit experiment. Imagine a wall with two narrow openings cut into it. Behind the wall sits a detector screen waiting quietly in darkness. If you send ordinary waves through the openings, like water waves, they spread outward and overlap. Where peaks meet peaks, the waves strengthen. Where peaks meet valleys, they weaken. The result is an interference pattern, alternating bright and dark regions. Light creates exactly the same pattern. But here is where things begin to feel almost impossible. Even if scientists send photons one at a time, separated so carefully that each photon crosses alone, the interference pattern still slowly appears over time. It is as though each photon somehow behaves like a spread-out wave while travelling, exploring multiple possibilities at once before finally arriving at a single location. The deeper one stares into this experiment, the more reality itself begins to feel less solid than everyday life suggests. And because of this, some physicists eventually began asking a strange question. What if photons are not truly tiny objects moving through space at all? What if light is something softer, less permanent, more like a temporary disturbance inside a deeper structure? Modern quantum field theory leans gently in this direction. According to this picture, the universe is filled with invisible fields extending everywhere. There is an electron field, a quark field, an electromagnetic field. What we call particles may actually be localized excitations inside those fields, temporary ripples moving through something more fundamental underneath. In this view, a photon is not a miniature glowing marble racing across emptiness. It is a ripple in the electromagnetic field itself, like a wave moving across the surface of a dark ocean. And perhaps this is part of why light feels so elusive. We instinctively want objects to behave like tiny solid things with permanent identities. But light resists being pinned down in that way. It spreads like a wave, arrives like a particle, behaves statistically, exists probabilistically, and may ultimately be less like an object and more like an event, a temporary pattern, a moving disturbance, a brief shape formed inside the fabric of reality. There is something oddly calming about that idea, because the universe itself may work less like a machine built from rigid pieces and more like music unfolding through vibration and relationship. Even matter begins to look different through this lens. Atoms are mostly empty space. Particles flicker in and out through quantum fluctuations. Fields overlap continuously through the vacuum. Stability itself becomes something dynamic, patterns holding together for a while, rather than permanent structures frozen forever. And light may be the purest example of this fluidity. A photon can cross billions of light years without aging internally, not because it is immortal in the ordinary sense, but because it may not be the kind of thing we usually imagine at all. The ancient light reaching your eyes tonight could be understood as a ripple still moving through the electromagnetic field after nearly the entire history of the cosmos unfolded around it. Not a tiny traveller carrying luggage through empty darkness, but a persistent vibration crossing an evolving universe. This perspective also changes the emotional meaning of redshift. If photons are ripples moving through space-time, then cosmological redshift becomes less like a particle losing strength and more like a wave being stretched as the medium beneath it changes, like music slowing as a record player gradually loses speed, or long ocean swells widening as they move into deeper water. The photon itself does not decide to weaken. The geometry beneath the ripple evolves, and once you begin seeing light this way, the universe starts feeling less like a collection of separate objects drifting through emptiness, and more like one immense connected process unfolding slowly through time. Galaxies, stars, planets, radiation, quantum fields, all participating in the same cosmic structure, all influencing one another through invisible relationships stretching across unimaginable distances, which means the ancient photons arriving from the edge of the observable universe are not merely showing us distant objects, they are carrying the fingerprints of space-time itself, and as those fingerprints slowly stretch and soften during the journey, another layer of the mystery quietly comes into view. Because if light is shaped by the expansion of the universe itself, then perhaps the darkness between galaxies is not truly empty after all. Perhaps space itself is alive with motion. For most of human history, the universe seemed steady. The stars rose each evening in familiar patterns. The moon returned in predictable cycles. Even when people imagined the cosmos as enormous, it still felt permanent, like a grand stage that had always existed exactly as it appeared. And in many ways, our everyday experience still whispers the same assumption to us now. Rooms stay where they are. Roads do not silently grow longer overnight. Cities do not drift apart while we sleep. Space feels fixed and unmoving, like an invisible container holding reality in place. Which is why one of the greatest discoveries of modern science feels so difficult to emotionally absorb, even after you understand the mathematics behind it. The universe itself is expanding, not simply the galaxies moving through space like sparks flying outward from a firework, but space itself quietly stretching between them. This distinction is subtle at first, but once you begin to feel it properly, the entire universe changes shape in your mind. In the early 20th century, astronomers began carefully studying light arriving from distant galaxies. By spreading that light into spectra, delicate bands of colour carrying hidden information, they discovered something astonishing. Most galaxies appeared shifted toward redder wavelengths. The farther away the galaxies were, the stronger this redshift became. At first glance, it resembled an ordinary Doppler effect. You've heard this phenomenon many times without thinking about it. An ambulance siren sounds higher as it approaches, then drops lower as it drives away. The sound waves compress ahead of the moving vehicle and stretch behind it. Light can behave similarly. If an object moves away through space, its light stretches toward redder wavelengths. But the deeper astronomers looked, the stranger the situation became. It was not merely that galaxies were travelling through a static universe. The structure of the universe itself appeared to be changing over time. To understand why this matters, it helps to let go of the idea that space is simply nothing. We often imagine emptiness as a blank stage upon which matter moves, but in relativity, spacetime behaves more like an active fabric, something capable of bending, stretching, and evolving. A useful image is the surface of rising bread dough. Imagine placing small raisins throughout the dough before baking it. As the dough rises in the oven, every raisin sees the others drifting farther away. Not because the raisins are crawling through the dough, but because the dough itself is expanding between them. From any individual raisin, it appears as though all the others are receding, and importantly, there is no special center. Every location experiences the same overall stretching. The universe behaves in a surprisingly similar way. Galaxies are often not racing through space under their own motion across vast cosmic scales. Instead, the distance between galaxies grows because space-time itself slowly expands. The road becomes longer while the travellers remain mostly where they are. This is one reason astronomers sometimes describe galaxies as carried along by the expansion of the universe. There is a soft sadness hidden inside that image. Entire galaxies, each containing billions or even trillions of stars, drifting apart not through intention or force, but because the universe itself is quietly unfolding outward beneath them. And unlike an ordinary explosion, the expansion does not require empty space outside the universe for it to grow into. That question naturally appears in many minds. What is the universe expanding into? But according to modern cosmology, the expansion is not occurring inside some larger external emptiness. Space itself is what expands. Distances grow internally within the structure of the cosmos, like points drawn on the surface of a balloon becoming farther apart as the balloon inflates, even though the two-dimensional creatures living on that surface would never need to imagine a separate outside direction in order for their world to grow. Of course, every analogy eventually bends under the weight of reality. Balloons have centres. Dough expands into kitchens. real spacetime is far stranger than household objects. Still, these gentle comparisons help the mind loosen its grip on ordinary intuition, because once space itself becomes dynamic, many mysteries begin quietly falling into place, including redshift. Imagine drawing a smooth wave across an elastic sheet. If the sheet stretches while the wave travels, the distance between each crest widens too. The wave becomes longer without the wave itself actively deciding to change. Cosmological redshift works in much the same way. As photons cross the expanding universe, the space-time beneath them slowly stretches. Their wavelengths lengthen along with it. Blue light drifts toward red. Visible light may soften into infrared radiation. Ancient radiation from the early universe stretches all the way into microwaves. The photon continues travelling exactly as light always does. But the geometry surrounding the journey evolves continuously. This is why cosmological redshift differs from ordinary Doppler motion. The light is not merely reacting to galaxies speeding through a fixed emptiness. The universe itself is changing scale during the journey. And hidden inside that stretching is one of the most important measurements in all of astronomy. The farther away a galaxy is, the more its light has stretched, and therefore the more the universe has expanded while that light travelled toward us. In this way, light becomes a kind of cosmic ruler, or perhaps more poetically, a memory that physically changes shape while crossing time. Astronomers eventually discovered that this expansion follows an overall relationship now known as the Hubble-Lemaitre law. In simple terms, more distant galaxies generally recede faster because more expanding space exists between us and them. Not because Earth occupies some privileged centre, but because expansion occurs everywhere at once. Like tiny boats drifting apart across a slowly widening sea, and perhaps this is where the emotional meaning of cosmology begins quietly changing: the night. Sky no longer appears as a static ceiling filled with fixed stars. Instead, it becomes dynamic, living, evolving. The darkness between galaxies is not passive emptiness. It is active geometry, continuously reshaping the journeys of light itself. Every ancient photon crossing the universe must travel through this stretching sea of space-time, and over billions of years. The universe leaves its fingerprints on every beam. The light arriving tonight from distant galaxies is not exactly the same light that first departed long ago. The cosmos has been gently pulling at it the entire way, and soon, those stretched fingerprints will begin telling us something even more extraordinary. Because hidden inside redshifted light is the history of the universe itself. Imagine listening to a favourite song on an old cassette player late at night. At first, the music sounds normal. The singer's voice rises clearly through the quiet room. The rhythm moves gently forward. Every note arrives exactly where you expect it to. But then the batteries begin to weaken. Almost too slowly to notice, the song starts stretching. The tempo softens, voices deepen, the spaces between sounds grow longer, nothing in the melody itself intended to change, and yet the entire experience gradually becomes lower, slower, heavier. In a strangely similar way, this is what happens to light crossing the expanding universe. The photon itself does not become damaged or exhausted internally. It does not slowly wear out like a machine aging over time. Instead, the structure of space-time stretches beneath the journey, gently pulling the light wave wider and wider as it travels, and that widening changes everything. Light behaves as both particle and wave. When scientists describe the wavelength of light, they are talking about the spacing between repeating peaks in that wave. Short wavelengths correspond to higher energy light, such as blue light, ultraviolet radiation, or X-rays. Longer wavelengths correspond to softer, lower energy forms like red light, infrared radiation, microwaves, and radio waves. You can think of it almost like musical pitch. Short, tightly packed waves resemble high notes on a piano. Longer waves resemble lower, deeper tones played more slowly. As space expands, the wavelength of light stretches along with it. The notes of the universe gradually deepen. This process is called cosmological redshift because the light drifts toward the red end of the visible spectrum. But in reality, many ancient photons are stretched far beyond visible red light entirely. Some continue into infrared wavelengths invisible to human eyes. Others stretch into microwave radiation so gentle and cold that special instruments are required to detect them at all. The oldest surviving light in the universe has been stretched this way for nearly 14 billion years. And through that immense journey, the universe itself has continuously reshaped the light. There is something deeply poetic hidden in this idea, because redshift means that distance is not passive. Travel changes the message. The farther light moves through the cosmos, the more the cosmos changes the light itself. If a photon leaves a distant galaxy carrying brilliant blue radiation, it may arrive billions of years later as faint reddish infrared light. The information survives, but transformed. Like a photograph slowly fading while crossing generations. Or like a voice recording stretched thinner each time it is copied. This stretching also affects the energy carried by light. The energy of a photon is connected to its frequency, meaning how rapidly the wave oscillates. Higher frequency light carries more concentrated energy. Lower frequency light carries less. As expanding space stretches wavelengths farther apart, the frequency decreases as well. The rhythm of the wave softens. The energy becomes gentler, and so ancient photons slowly lose energy during their cosmic journey. This creates one of the strangest emotional tensions in all of cosmology. The photon never experiences internal aging, yet the universe still changes its energy. At first glance, this almost feels impossible. We instinctively imagine energy behaving like money stored safely in a vault. If energy disappears, surely it must go somewhere. But in an expanding universe, the situation becomes subtler than ordinary intuition expects. On local scales, the laws of physics conserve energy beautifully. Energy moves between forms, motion becomes heat, electricity becomes light, mass becomes radiation. But across the evolving geometry of the entire universe, the old simple picture becomes less absolute. The expanding cosmos does not behave like a closed mechanical box sitting quietly in emptiness. Space-time itself evolves, and because the geometry changes, the energy carried by light changes along with it. This does not mean the laws of physics are broken. Rather, it reveals that the universe is stranger and more dynamic than everyday experience prepares us for. In some sense, the photon's lost energy does not go anywhere at all. The expanding geometry simply changes the relationship between the wave and the universe through which it travels. That realization can feel deeply unsettling for a moment, almost like discovering that reality itself is less solid than expected. But there is also something oddly peaceful about it. The universe is not rigid machinery. It is process, change, continuous unfolding. Even emptiness participates. And because of this stretching, ancient light becomes an extraordinary tool for understanding cosmic history. Every redshifted photon carries information about how much the universe expanded during its journey. The more stretched the wavelength becomes, the more space-time changed between emission and observation. Astronomers measure this stretching carefully using what is called redshift value. But rather than thinking of it as a dry number, it is more helpful to imagine it as a kind of cosmic timestamp, a measure of how different the universe became while the light was travelling. A tiny redshift corresponds to relatively nearby galaxies. Large redshift values correspond to ancient light emitted when the universe was far younger, denser, and hotter than it is now. In this way, light becomes more than illumination. It becomes archaeology. The night sky transforms into layers of preserved history stacked across distance and time. Nearby stars reveal the recent universe. Distant galaxies reveal ancient epochs. And the faint microwave glow surrounding the cosmos reveals a time before stars even existed. All of it encoded into stretched wavelength, quietly drifting through darkness. Sometimes it helps to imagine the observable universe less as a collection of places and more as a vast archive of travelling memories. Every photon arriving here tonight began its journey inside conditions that no longer exist. Some left galaxies that have since collided and transformed completely. Others departed before Earth formed. Some were emitted when the universe itself was young enough that the first generations of stars were only beginning to ignite. And all along the way, expanding spacetime slowly altered the rhythm of those ancient waves. The cosmos reshaped its own memories while carrying them forward, which means that when astronomers observe redshift, they are not merely measuring distance, they are measuring transformation. And soon, those transformed wavelengths will begin revealing another astonishing truth. The farther we look into space, the farther backward we look into time itself. If you've ever walked into a dark kitchen at night and recognized someone not by their face, but by the sound of their footsteps, then you already understand something important about astronomy. Much of science is the art of identifying things indirectly. Astronomers cannot reach out and touch distant galaxies. They cannot collect stars in glass containers or hold ancient nebulae beneath laboratory lamps. Nearly everything we know about the wider universe comes from interpretation, from carefully studying the light that arrives after unimaginably long journeys through space, and hidden inside that light are patterns, tiny repeating structures, almost like fingerprints, quietly revealing what created the light in the first place. These patterns are called spectral lines. At first glance, a beam of light may appear simple and continuous. White sunlight spilling across a window seems smooth and uniform. But if that light is spread apart through a prism or scientific instrument, it separates into bands of colour. Within those bands, thin dark gaps and bright lines appear in precise locations. Those delicate markings are not random. Every chemical element interacts with light in its own unique way. Hydrogen absorbs and emits certain wavelengths. Helium leaves behind a different arrangement. Oxygen, carbon, sodium, iron. Each produces its own characteristic pattern, like musical instruments producing recognizable tones even when playing the same melody. Atoms leave behind identifiable signatures in light. And astonishingly, those signatures appear everywhere in the universe. The hydrogen inside a distant galaxy billions of light years away behaves according to the same physical laws as hydrogen inside a laboratory on Earth. This consistency is one of the quiet miracles of modern science. The cosmos is vast beyond imagination, yet governed by patterns that repeat with extraordinary precision. Astronomers sometimes describe these spectral patterns as cosmic barcodes, and in many ways that comparison is beautifully accurate. Just as a barcode in a grocery store identifies an object instantly through hidden information, spectral lines allow scientists to identify the composition, temperature, motion, and even history of distant stars and galaxies using nothing but light. But redshift changes those patterns in a very particular way. Imagine taking a familiar piano melody and stretching every note farther apart while preserving the relationships between them. The song would sound deeper and slower, but the underlying structure would remain recognizable. Cosmological redshift behaves similarly. The spectral fingerprints remain intact, but the entire pattern shifts toward longer wavelengths. Hydrogen still looks like hydrogen. Its fingerprint simply arrives stretched. This stretching allows astronomers to measure how much the universe expanded during the photon's journey. The farther the spectral lines shift, the longer the light has travelled through expanding spacetime. And this is where spectroscopy becomes one of the most powerful tools ever developed by human beings. Using nothing more than ancient photons, scientists can reconstruct the history of the cosmos. They can determine whether galaxies are approaching or receding. They can estimate immense distances. They can identify elements forged inside stars billions of years ago. They can even study invisible gas drifting between galaxies by observing tiny absorption marks left on passing light. All from patterns hidden inside waves. There is something deeply intimate about this process. The universe speaks softly, not through dramatic explosions alone, but through delicate shifts in frequency, faint dark lines, tiny distortions inside light crossing the dark, and humanity learned how to listen. In recent years, instruments like the James Webb Space Telescope have carried this listening ability farther than ever before. Unlike the Hubble Space Telescope, which primarily observed visible and ultraviolet light, Webb was designed to see deeply into infrared wavelengths, precisely because ancient light arrives heavily redshifted. Some of the earliest galaxies in existence no longer appear visible at ordinary wavelengths. Their light has stretched too far during its cosmic journey. What once may have shone brilliantly in ultraviolet radiation now reaches us as faint infrared whispers. It is almost like hearing the slowed echoes of a younger universe. Webb's mirrors and infrared instruments allow astronomers to detect these stretched signals with astonishing sensitivity. Galaxies born only a few 100 million years after the Big Bang emerge from darkness as dim reddish smears. Ancient structures barely distinguishable from the blackness surrounding them, and yet those faint signals carry extraordinary stories. Inside them are clues about the first generations of stars, the early formation of galaxies, and the gradual transformation of the universe from a hot glowing plasma into the richly structured cosmos we inhabit now. One particularly mysterious region in cosmic history became known informally as the Redshift Desert. For many years, astronomers struggled to observe certain distant epochs clearly because the spectral signatures shifted into difficult observational ranges. It was as though a stretch of cosmic history hid behind fog. But advances in infrared astronomy have slowly begun illuminating this missing era. New telescopes and observational techniques are helping scientists map the transition between the first stars and the mature galaxies that followed. The darkness is becoming readable. And perhaps that phrase captures the emotional essence of astronomy better than any technical definition ever could. To study redshift is to study readability across distance and time. The farther light travels, the more difficult the message becomes to interpret. Wavelengths stretch, signals weaken, information softens into faint traces nearly swallowed by cosmic noise. Yet against overwhelming odds, meaning survives. Ancient photons still carry recognizable fingerprints across billions of years, even after crossing expanding space-time for nearly the age of the universe itself. The patterns remain decipherable. There is something profoundly moving about that resilience, a quiet persistence built into reality itself. The stars leave signatures behind. The universe stretches them gently across time, and somehow, they still arrive. Sometimes when astronomers analyze spectra from unimaginably distant galaxies, they are effectively studying light that began traveling long before Earth existed, before mountains rose, before oceans settled, before life learned to breathe beneath the sun. Those photons crossed an evolving universe carrying encoded information through darkness, almost beyond comprehension. And tonight, some tiny fraction of that ancient journey ends quietly inside human instruments or human eyes. A species made of atoms forged inside stars learning to decode the fingerprints of light, and as those fingerprints continue guiding us deeper into cosmic history, another realization begins slowly unfolding from the darkness. Looking farther into space is not merely looking across distance, it is looking backward through time itself. When you stand outside on a clear night and look toward the stars, it is easy to feel as though you are seeing the universe exactly as it exists in this moment. The sky appears immediate, present, alive right now above your head, but light moves at a finite speed, and the universe is so enormous that even light requires time to cross it. Not minutes or hours, but years, centuries, millions of years, and because of this, every glance into deep space is also a glance into the past. Moonlight takes a little over 1 second to reach Earth. When you look at the moon, you are seeing it not as it is now, but as it was just over a second ago. Sunlight takes about 8 minutes to arrive here. If the sun could somehow vanish instantly, Earth would continue peacefully orbiting for those final silent minutes before darkness arrived. The nearest stars beyond our sun are seen years in the past. Nearby galaxies are seen millions of years ago, and the deepest objects observed by modern telescopes appear as they existed billions of years before human beings ever walked the Earth. Distance becomes time. The universe quietly turns space into memory. This realization changes the emotional feeling of astronomy completely. Telescopes are no longer merely instruments for looking far away. They become machines for looking backward through cosmic history. Every increase in observational distance pushes us deeper into earlier eras of the universe. Nearby stars reveal a relatively recent cosmos. Farther galaxies reveal younger cosmic epochs, and the faintest detectable light carries us astonishingly close to the beginning itself. Imagine standing beside a vast dark ocean at night. Close to shore, the waves are recent and familiar, but farther outward, beyond the visible darkness, ancient swells continue travelling toward you from storms that formed long ago. The universe behaves in a surprisingly similar way. Ancient photons continue arriving from increasingly distant regions of spacetime, carrying images of a cosmos that no longer exists in the form we observe. Some galaxies we see in deep-field telescope images have changed dramatically since emitting the light now reaching us. Many have merged with neighbouring galaxies. Some no longer exist as separate structures at all. Others may have evolved from chaotic star-forming systems into enormous mature spirals or elliptical galaxies over billions of years. The light arrives carrying an old version of reality, and because the farther objects appear more heavily redshifted, astronomers can estimate roughly how ancient those visible moments truly are. In this sense, redshift becomes more than a measure of distance, it becomes a measure of cosmic age. A photon stretched strongly toward red tells us it has crossed an enormous amount of expanding space-time. It comes from an era when the universe was much younger, denser, and hotter than today. And this allows astronomers to reconstruct the broad timeline of cosmic evolution. At first, after the Big Bang, the universe was unimaginably hot and dense. There were no stars, no planets, no galaxies, only an expanding sea of energy and particles too energetic for stable atoms to exist. As expansion continued, the universe cooled. Eventually atoms formed, then darkness, a vast era before stars existed at all. Gravity slowly gathered matter into denser regions over millions of years, like invisible snowfall collecting quietly in valleys. Gradually the first stars ignited. their light began pushing outward through the darkness for the first time. Those earlier stars were likely very different from the Sun. Many were enormous, unstable, and intensely bright. They lived quickly and died violently, forging heavier elements that later generations of stars and planets would inherit. In a very real sense, your body contains atoms born inside ancient stellar furnaces that illuminated the young universe long before Earth existed. Carbon in your cells, oxygen in your lungs, iron in your blood, all forged inside stars whose light once travelled outward into the cosmic night. There is something deeply comforting about that continuity. Human beings often feel small beneath the stars, but the matter composing us is inseparable from cosmic history itself. And through Redshift, astronomers can actually observe many stages of that unfolding story. One of the most extraordinary achievements of modern astronomy has been the creation of deep field observations. Telescopes stare at tiny, seemingly empty patches of sky for days or weeks, collecting faint photons arriving one by one from immense distances. At first glance, those images can appear almost abstract. Tiny reddish smudges scattered through darkness, but each faint blur may contain billions of stars, entire galaxies hidden inside what initially looked like emptiness. And because the light from the most distant galaxies has travelled for so long, these observations effectively reveal the early universe itself. Some galaxies observed by the James Webb Space Telescope appear from periods only a few 100 million years after the Big Bang, astonishingly early in cosmic history. To appreciate how remarkable that is, imagine compressing the nearly 14 billion year history of the universe into a single calendar year. In that scale, modern civilization appears only during the final seconds before midnight on December 31st, yet Redshift allows us to look backward almost all the way toward the beginning of that cosmic calendar. Not perfectly, of course. There are limits. Eventually, if we look far enough into the past, we encounter a barrier beyond which ordinary visible light cannot travel freely. Earlier than that point, the young universe remained filled with hot charged particles scattering light continuously, making space opaque like dense fog. But before reaching that ancient wall, Redshift still grants us access to immense stretches of cosmic history. It transforms the sky into layered time, and perhaps this is why astronomy feels emotionally different from many other sciences. Most sciences study objects in the present moment. Astronomy studies preserved history still arriving from far away. The night sky's filled with delayed messages, some ancient, some recent, some emitted before Earth formed, and all of them travelling through an evolving universe that continuously reshapes the light along the way. There is a strange tenderness hidden in that image, because every photon reaching us tonight survived an extraordinary journey through expanding darkness. It crossed billions of years without resting, carrying fragile information across a universe constantly changing beneath it. And as we continue tracing those ancient signals farther backward through time, eventually we arrive at the oldest surviving light of all, a faint cosmic glow left behind when the universe itself was still young enough to shine like fire, long before stars illuminated the darkness, before galaxies spiraled quietly through space, before planets formed oceans beneath young suns. The universe itself glowed, not in scattered points like the night sky we know today, but everywhere at once. The young cosmos was filled with intense heat and brilliant radiation, dense, beyond ordinary imagination. Matter and light existed together in a turbulent sea so energetic that stable atoms could not yet survive. Electrons moved freely, photons scattered constantly in every direction. Space itself resembled a glowing fog without clear transparency. In that ancient era, light could not travel very far. A photon would move briefly before colliding again with charged particles surrounding it. Then another collision, and another, again and again, endlessly scattered through the hot plasma of the early universe. You can imagine trying to shine a flashlight through thick white fog late at night. The light does not travel cleanly forward. It bounces and diffuses, becoming trapped inside the mist. The early universe behaved similarly. For hundreds of thousands of years after the Big Bang, the cosmos remained opaque. And then, slowly, everything changed. As space-time expanded, the universe cooled. Temperatures dropped enough for electrons and atomic nuclei to combine into stable atoms for the first time. Suddenly, photons were no longer trapped in constant collisions. Light could finally move freely across vast distances. The cosmic fog cleared, and the radiation released during that moment still travels through the universe today. This ancient glow is known as the cosmic microwave background, often shortened simply to the cosmic background radiation. It is the oldest light human beings have ever observed. Not the oldest stars, not the oldest galaxies, but the oldest surviving photons still moving freely through the cosmos. The light began its uninterrupted journey nearly 14 billion years ago, and tonight, some tiny fraction of it still passes quietly through your body. There is something almost impossible about that thought. Ancient radiation released when the universe itself was still in cosmic infancy, still drifting through space after all this time. When scientists first discovered this faint background glow in the 1960s, it arrived unexpectedly. Two radio astronomers working with a large antenna kept detecting a persistent low-level microwave signal, no matter where they pointed the instrument. At first, they suspected technical problems. They cleaned equipment carefully. They investigated interference sources. They even removed pigeons nesting inside the antenna structure, worried that ordinary contamination might explain the mysterious signal. But the faint radiation remained. Eventually, researchers realized they had stumbled upon one of the greatest discoveries in cosmology. The universe itself was still glowing faintly from its early hot state. The Big Bang had left behind a fossil light, and over billions of years of cosmic expansion, that once blazing radiation had been stretched enormously by redshift. Originally, the early universe glowed at temperatures far hotter than the surface of the sun. The radiation would have appeared brilliant and intense, more like dazzling visible or infrared light. But as space-time expanded, the wavelength stretched continuously. The universe gently pulled the radiation apart. Today, that ancient light has cooled to only a few degrees above absolute zero, incredibly faint and soft. Instead of visible brightness, it now arrives primarily as microwave radiation, detectable only with sensitive instruments. The oldest light in existence no longer shines, it whispers. And perhaps no discovery illustrates cosmological redshift more beautifully than this one. The cosmic microwave background is ancient light physically transformed by the expansion of the universe itself. The photons survived, but the geometry around them changed. Over nearly 14 billion years, the wavelength stretched thousands of times larger than when they first began travelling freely through space. The energetic glow of the young universe softened into cold microwaves drifting silently through darkness. It is almost like listening to the fading echo of a bell rung at the beginning of time, and hidden inside that ancient radiation are tiny fluctuations. Delicate variations in temperature so small they are almost difficult to comprehend. Some regions appear ever so slightly warmer, others slightly cooler. Those minute differences matter enormously because they represent the earlier seeds of structure in the universe. Tiny density variations in the young cosmos eventually grew under gravity's influence, over immense spans of time, they became galaxies, clusters, stars, planets, and eventually living beings capable of wondering where they came from. In a very real sense, the cosmic microwave background is not merely ancient radiation, it is a baby photograph of the observable universe, a preserved snapshot from an era long before galaxies fully formed. Modern missions studying this ancient light have mapped these fluctuations with astonishing precision. Satellites like COBE, WMAP, and Planck transformed cosmology into an extraordinarily accurate science by measuring the subtle structure hidden inside the background radiation. And from those tiny patterns, scientists could estimate the age of the universe, the overall geometry of space-time, the amount of ordinary matter, the influence of dark matter, and the mysterious role of dark energy in cosmic expansion, all encoded inside faint microwave light, crossing the universe since its earliest ages. There is something deeply humbling about that. Humanity evolved on a small rocky planet orbiting an ordinary star, and yet managed to decode the thermal afterglow of the early cosmos itself. But emotionally, perhaps the most haunting aspect of the cosmic microwave background is what it reveals about memory, because this radiation has been travelling toward us almost since the beginning. The universe has changed unimaginably during that time. Galaxies formed, stars exploded, black holes emerged, entire generations of cosmic structure appeared and disappeared. Yet these ancient photons continued quietly forward through expanding space-time, timeless travellers crossing a transforming universe. And just as cosmological redshift softened their energy over billions of years, the future will continue stretching them even farther. One day, trillions of years from now, the cosmic microwave background may become so stretched and diluted that future civilizations cannot detect it at all. The evidence of the universe's hot beginning could fade completely from observation. The sky would appear darker, quieter, more empty. And the ancient glow revealing the birth of the cosmos would dissolve into wavelengths too enormous and weak to measure, which means that right now, in this brief era of cosmic history, we live at a very unusual moment. The universe is old enough for stars, planets, chemistry, and life to exist, but still young enough that its earliest light remains visible. We inhabit a narrow window where the cosmos can still remember itself clearly. And beyond that ancient microwave glow, another mystery continues waiting in the darkness. Because the expansion responsible for stretching all this light is not slowing down, it is accelerating. There are moments in science when a discovery does more than answer a question. It changes the emotional shape of reality itself. Before the 20th century, many scientists believed the universe was eternal and largely unchanging on the larger scales. Stars and galaxies might evolve locally, of course, but the cosmos as a whole was often imagined as static, suspended in a kind of grand balance beyond time. Even Albert Einstein initially preferred this picture. When he first applied general relativity to the universe itself, the equation suggested something deeply uncomfortable. Space-time should either expand or contract. Gravity would not allow the cosmos to remain perfectly still forever. That unsettled him. To preserve a static universe, Einstein introduced an additional mathematical term into his equations, a kind of balancing effect intended to hold the cosmos steady against gravitational collapse. But the universe, quietly and indifferently, had other plans. Around the same period, astronomers were beginning to study distant spiral nebulae, objects once thought to be small clouds within our own galaxy. One of these astronomers was Vesto Slipher, working patiently at Lowell Observatory in Arizona during the early 1900s. Night after night, Slipher measured the spectra of these distant objects. And hidden inside the light, he found something astonishing. Most of the nebulae appeared redshifted. Their spectral fingerprints were shifted toward longer wavelengths, suggesting they were moving away from Earth at enormous speeds. At first, the implications were difficult to fully absorb. The universe was far larger than people had imagined. These nebulae were not nearby clouds. They were entire galaxies, immense islands of stars drifting through deep space, and most of them seemed to be receding. Later, Edwin Hubble expanded upon these observations using more precise distance measurements. He discovered a remarkable pattern. The farther away a galaxy appeared, the greater its redshift tended to be. Distance and recession were connected. The universe was expanding, not in some violent explosion outward from a central point, but everywhere at once, through the stretching of spacetime itself. It is difficult to overstate how profoundly this transformed humanity's understanding of existence. Suddenly, the universe had history. If galaxies are moving apart now, then long ago they must have been closer together. Follow the expansion backward far enough, and the cosmos becomes hotter, denser, and more compressed. The modern picture of cosmic evolution began emerging from this realization, and redshift was the key. Tiny stretched wavelengths hidden inside ancient light revealed that reality itself evolves over time. There is something almost delicate about that fact. The discovery did not arrive through giant cosmic explosions visible to the naked eye. It emerged from subtle shifts in spectral lines, tiny distortions in light carefully measured through glass instruments under quiet observatory domes. Human beings discovered the expansion of the universe by noticing that ancient light arrived slightly redder than expected. A whisper changed cosmology. And for much of the 20th century, scientists assumed that although the universe was expanding, gravity should gradually slow that expansion over time. After all, gravity pulls matter together. Galaxies attract one another. Large structures form through gravitational collapse. It seemed natural to imagine cosmic expansion steadily decelerating like a ball tossed upward against Earth's gravity. But then came another extraordinary surprise. In the late 1990s, astronomers studying distant supernova explosions discovered that the universe was not slowing its expansion, it was accelerating. The farther researchers looked into deep space, the stranger the expansion history became. Distant supernova appeared dimmer than expected, implying that the universe had expanded more during the photon's journey than older models predicted. Something seemed to be pushing space-time apart faster and faster over time, and whatever this influence was, it appeared to dominate the large-scale future of the cosmos itself. Scientists eventually gave this mystery a simple name: dark energy. Even now the phrase carries a certain haunting vagueness. It sounds almost poetic, like something hidden behind the visible world. But in truth, the name reflects deep uncertainty. Dark energy is not fully understood. It represents our label for the observed acceleration itself, the unseen influence causing expansion to speed up across immense cosmic scales. And because of dark energy, the future of the universe changes dramatically. Without accelerated expansion, distant galaxies might remain visible indefinitely, their light continuing to drift slowly across space. But with acceleration, entire regions of the cosmos gradually slip beyond reach. The expanding sea of space-time grows faster and faster between faraway galaxies. Eventually, some distant light can no longer make progress toward us overall, because new space forms too rapidly along the journey. This does not violate relativity, because galaxies are not outracing light through local space in the ordinary sense. Instead, space-time itself expands between distant regions. The road grows faster than the traveller can cross it. There is something quietly heartbreaking about this image. galaxies filled with stars, planets, perhaps even life, slowly disappearing beyond a cosmic horizon not through destruction, but through distance becoming insurmountable, light losing the race against space, and all of this was uncovered through Redshift. The stretching of ancient photons revealed not only that the universe expands, but that the expansion itself evolves over time. Today, astronomers continue refining these measurements using increasingly sophisticated instruments. Giant galaxy surveys map millions of redshifts across cosmic space. Observatories track subtle patterns in large-scale structure. Space telescopes examine distant supernovae and ancient galaxies in extraordinary detail, and yet the deeper measurements become the stranger universe sometimes appears. Different methods for measuring cosmic expansion now produce slightly conflicting answers. Some measurements based on the early universe suggest one expansion rate. Measurements based on nearby galaxies suggest another. This growing puzzle has become known as the Hubble tension. It may eventually lead to new discoveries about dark energy, space-time, or the underlying structure of cosmology itself. Or perhaps it will reveal hidden complexities in measurements we do not yet fully understand. Either way, the story is still unfolding. The universe continues surprising us, and perhaps that uncertainty is part of what makes cosmology feel so human. We're trying to understand a structure vastly larger and older than ourselves, using tiny stretches of ancient light arriving across billions of years. And somehow, against extraordinary odds, those photons still carry enough information for us to glimpse the architecture of the cosmos. The universe speaks in stretched wavelengths, and we are slowly learning how to listen. But as expansion accelerates farther into the future, another realization begins quietly emerging from the darkness. There may come a time when the universe grows too large for most of its own history to remain visible at all. Imagine standing in the ocean at dusk. At first, the water feels calm around you. Small waves move gently past your legs. The shore remains comfortably visible behind you. Swimming outward seems easy enough, but farther from land, the current quietly strengthens. You continue moving forward with steady effort, yet the water beneath you begins carrying everything backward faster and faster. Eventually, there comes a subtle, invisible boundary where swimming harder no longer helps. Beyond that point, the ocean itself pulls the distance open faster than you can cross it. In a strangely beautiful way, something similar may be happening across the universe. For billions of years, light has travelled through expanding space-time, carrying messages between galaxies. Ancient photons crossed enormous distances, allowing the cosmos to remain connected through visibility and information. Even when galaxies drifted apart, their light could still continue bridging the darkness between them. But dark energy changes the story. Because the expansion of the universe is accelerating, some regions of space-time are now separating so rapidly that light emitted today may never successfully reach certain destinations in the future. Not because light has slowed down, not because photons became weak, but because the fabric of space itself keeps stretching faster and faster during the journey. This leads to one of the strangest ideas in modern cosmology: a cosmic event horizon. The phrase sounds dramatic, almost like the edge of a black hole, but the underlying idea is gentler and quieter. A cosmic horizon is not a wall hanging somewhere in space. There is no glowing boundary or physical barrier waiting in the darkness. Instead, it is a limit created by expansion itself. Beyond certain immense distances, galaxies recede in such a way that their future light can no longer overcome the growth of space-time between us. You can picture it like footprints forming in wet sand while the beach stretches beneath your feet. At first, each step leaves a visible trail behind you, but eventually the ground itself expands so quickly that the spacing between footprints grows faster than new steps can connect them. The path breaks apart. Light faces a similar struggle across cosmic scales. This idea initially sounds as though it violates relativity. After all, haven't we learned repeatedly that nothing can move faster than light? Yes, locally that remains true. Nothing travels through nearby space faster than light itself. But cosmological expansion is different. Galaxies are often not speeding through space in the ordinary sense. Instead, new spacetime continuously forms between distant regions. The separation grows not because objects outrun light locally, but because the geometry connecting them evolves. It is the road itself that expands, and on sufficiently large scales, that growth can outpace the ability of light to close the distance. There is something emotionally strange about this realization. For most of human life, distance feels temporary. Given enough time, messages arrive. Travelers return home. Light from a lighthouse eventually reaches distant shores. But the accelerating universe introduces a new kind of separation, a permanent one. Some galaxies are not disappearing because their light stopped travelling, but because space keeps growing faster than the journey itself. Even now, many distant galaxies visible through modern telescopes have already crossed this threshold in a certain sense. We still see ancient light emitted long ago when those galaxies were closer, but the light they emit today may never reach us at all. The universe preserves old visibility while quietly preventing new communication. It is almost like watching the final delayed broadcasts from civilizations already drifting permanently beyond contact. And over unimaginably long spans of time, this isolation deepens. Billions and trillions of years into the future, most galaxies beyond our local gravitational neighborhood may vanish from view entirely. Their ancient photons will have either already arrived or become stretched beyond detectability by cosmic expansion. The night sky will slowly empty. Future observers living in distant ages may see only their own local galaxy, surrounded by immense darkness, unaware that countless other galaxies once filled the cosmos beyond sight. This possibility carries a quiet melancholy, because humanity currently lives during a remarkably fortunate era. The universe is old enough for large structures to exist, yet still young enough that light from distant galaxies continues reaching us. The observable cosmos remains richly populated with visible history. We can still trace cosmic expansion. We can still detect ancient radiation from the early universe. We can still read the stretched fingerprints carried by Redshift, but this window will not remain open forever. The observable universe is not a permanent archive. It changes continuously. And the farther dark energy drives cosmic acceleration, the more isolated each gravitationally bound region becomes. There is a haunting beauty in imagining the far future of astronomy. Future civilizations, if conscious life still survives somewhere, may inherit skies profoundly quieter than ours. No sprawling web of distant galaxies glowing across deep-field telescope images. No visible evidence of expansion across immense scales. No easy way to reconstruct the true history of the Big Bang. Their universe may appear static and lonely, not because the cosmos stopped evolving, but because expansion carried most visible history beyond reach. And yet, even in our present age, the effects of this cosmic isolation are already measurable. Astronomers studying distant supernova, galaxy distributions, and ancient background radiation continue mapping how expansion evolves over time. Enormous surveys observe millions of galaxies spread across cosmic space, tracing the large-scale geometry of the universe itself, and within those measurements, subtle tensions have begun emerging. Different techniques sometimes suggest slightly different expansion histories. Certain observations hint that our understanding of dark energy may still be incomplete. Perhaps the acceleration changes over time. Perhaps hidden physics remains buried beneath the data. The universe may still be withholding part of the story. But even without every answer, the broader direction appears increasingly clear. The cosmos is expanding, the expansion is accelerating, and the visible universe is slowly fragmenting into isolated islands of light, separated by growing oceans of unreachable darkness. Still, the ancient photons continue arriving for now, timeless travellers crossing distances so immense that the human mind can barely hold them all at once. And hidden inside their stretched wavelengths, scientists have discovered something unexpected. The universe itself may not entirely agree with our current explanations of how fast it is growing. There is a comforting assumption many people carry about science, that eventually, if we gather enough information, the universe will settle into clarity, the numbers will align neatly, the equations will close gently around reality like perfectly fitted puzzle pieces. Uncertainty will shrink until only understanding remains. And sometimes science does feel that way, a gradual movement from confusion toward precision. But every so often, just when a theory begins appearing stable and complete, the universe quietly introduces a new wrinkle into the pattern, a small disagreement, a faint inconsistency, a whisper hidden inside the measurements. Modern cosmology may be entering one of those moments now. For decades, astronomers have worked carefully to measure the expansion rate of the universe as accurately as possible. This value, often called the Hubble constant, describes how quickly cosmic distances grow on large scales. In simple terms, it helps determine how fast galaxies drift apart through expanding spacetime. At first, measuring this rate was extraordinarily difficult. Distances across the universe are not marked with convenient signs or rulers. Astronomers had to develop delicate methods using variable stars, exploding supernovae, galaxy distributions, and ancient background radiation to estimate enormous cosmic scales indirectly. It was like trying to map an entire ocean using scattered echoes arriving through fog. Over time, the measurements improved dramatically. Space telescopes refined stellar distances. Giant galaxy surveys mapped the large-scale structure of the cosmos. Observatories studied ancient radiation from the early universe with astonishing precision. Piece by piece, humanity constructed an increasingly detailed picture of cosmic expansion. And then, the numbers stopped agreeing. Measurements based on the nearby universe began suggesting one expansion rate. Measurements based on the very early universe suggested another. Not wildly different, but persistently different, enough to make cosmologists pause. This growing discrepancy became known as the Hubble tension. The name sounds almost gentle, but beneath it lies a profound possibility. If the disagreement is real, it may mean that something important about our understanding of the universe is incomplete. Perhaps some hidden physical process subtly alters cosmic expansion over time. Perhaps dark energy behaves differently than expected. Perhaps the early universe evolved in ways current models do not fully capture. Or perhaps there are still unseen biases buried inside the measurements themselves. Tiny distortions introduced by instruments, assumptions, or statistical limitations. At the moment, no one knows for certain, and there is something strangely beautiful about that uncertainty, because it reminds us that cosmology is not a finished story carved permanently into stone. It is a living conversation between observation and mystery. In recent years, enormous observational projects have begun mapping the universe with unprecedented detail. Surveys observing millions of galaxies across cosmic time are tracing how large-scale structure evolved as space-time expanded. New instruments measure ancient light with extraordinary sensitivity. Space telescopes peer farther into redshifted history than previous generations could imagine, and instead of making the universe simpler, many of these observations have revealed additional subtleties. Some recent studies hint that dark energy may not remain perfectly constant across cosmic history. The acceleration of expansion might evolve gently over time, rather than behaving as a fixed background property of spacetime. If true, this would reshape our understanding of the future cosmos. It would mean the universe is even more dynamic than previously believed, not merely expanding, but changing the way it expands. The idea feels almost alive, as though spacetime itself carries rhythms we still do not fully hear. Of course, cosmologists remain cautious. Science moves carefully, especially when dealing with measurements across billions of light years. Extraordinary claims require extraordinary evidence. Many apparent mysteries in scientific history eventually dissolved once observations improved further. But even uncertainty has emotional weight, because for a brief moment, humanity stands at the edge of what it understands, listening carefully to faint disagreements hidden inside ancient light. And those disagreements emerge from photons that began their journeys billions of years ago. That fact alone is astonishing. Tiny stretched waves crossing cosmic darkness now shape debates about the ultimate structure and fate of the universe itself. It is difficult not to feel humbled by that, especially when we remember how indirect all of this truly is. No human being has touched dark energy. No one has held expanding spacetime in their hands. Everything we infer comes through interpretation, through patterns hidden inside redshift, brightness, temperature, and motion. We are reading the universe through traces carried by light, and perhaps reality is more layered than our current models can fully express. There is a tendency, especially in popular science, to imagine discovery as a straight path towards certainty, but actual scientific progress often feels softer than that, more patient, more human. A theory explains many observations beautifully, until new measurements reveal tiny tensions near the edges. Then understanding stretches, adapts, and deepens. The universe does not reveal itself all at once. It unfolds slowly, like distant mountains appearing gradually through morning fog, and perhaps this is especially true in cosmology, because the scales involved are so immense. Human intuition evolved for forests, rivers, weather, and seasons, not for expanding space-time billions of light years wide. Even concepts like dark energy or cosmic horizons already strain ordinary imagination. Trying to measure subtle changes in expansion history across nearly 14 billion years of cosmic evolution pushes the mind toward its natural limits. Yet still, humanity continues listening. New observatories now scan enormous regions of sky night after night, collecting ancient photons from galaxies scattered across the observable universe. Upcoming telescopes will refine these measurements further, tracing how structure formed and evolved through cosmic time. Each new observation acts almost like another note added to a vast unfinished symphony. Most of the melody already sounds coherent, but a few notes still feel unresolved. And somewhere inside those unresolved harmonies, there may be entirely new physics waiting quietly to emerge. Or perhaps the universe is teaching a gentler lesson, that reality itself is not obligated to become fully simple. That mystery is not a failure of science, but part of the experience of living inside an evolving cosmos. Either way, the broader arc remains clear. The universe expands, light stretches, ancient photons continue cooling as space-time grows, and over unimaginable ages this expansion slowly smooths away the energetic contrast that once filled the young cosmos with fire and brilliance. The universe, in a sense, is gradually softening itself, like tea left untouched overnight. slowly cooling towards stillness. If you leave a cup of tea untouched beside a window overnight, something subtle happens while you sleep. At first, the tea holds warmth gathered from boiling water. Steam rises softly into the air. Heat moves outward into the surrounding room. But hour by hour, the temperature differences slowly fade. By morning, the cup has settled into quiet balance with everything around it. No dramatic event occurs, no sudden transformation, only a gradual softening of contrast. In many ways, the universe appears to behave similarly. The early cosmos was a place of extraordinary intensity. Temperatures were unimaginably high. Matter and radiation existed in dense energetic motion. Stars ignited across darkness. Galaxies collided violently. Black holes fed upon swirling disks of superheated gas. Everywhere, energy differences drove structure, motion, chemistry, and light. But expansion changes the story. As spacetime grows, radiation stretches. Photon wavelengths lengthen. Energy becomes more diffuse. The universe cools, and over immense spans of time, the cosmos slowly spends its differences. This process is deeply connected to one of the most important ideas in physics, entropy. Now, entropy is often described in technical ways involving disorder, probability, or microscopic configurations of matter. Those descriptions are scientifically useful, but emotionally they can feel dry and distant. Perhaps a gentler image is more helpful here. Imagine dropping a pebble into a still pond at dusk. Ripples spread outward beautifully at first, creating distinct patterns across the water. But eventually the waves flatten. The differences between crest and trough slowly disappear. The pond returns toward stillness. Entropy is often the story of those differences fading over time. Hot regions cool, sharp contrasts soften. Energy spreads outward into larger and larger spaces, and because the universe itself expands continuously, this spreading process unfolds on truly cosmic scales. Ancient photons released billions of years ago continue stretching as they travel through space-time. Their wavelengths grow longer, their frequencies decrease, their energy softens, the universe cools itself by stretching its own light. There is something hauntingly elegant about that idea, because redshift is not merely changing colour, it is transforming the energetic character of reality itself. The early universe once blazed with intense radiation. Today, much of that ancient light survives only as faint microwave whispers drifting through near freezing darkness, and the process continues. Far into the future, even microwave radiation will stretch into vastly longer wavelengths. The cosmos will become progressively colder, dimmer, and quieter as expansion widens the distances between all things. This does not mean stars vanish immediately, of course. The universe still contains immense reservoirs of activity. New stars continue forming in galaxies. Black holes continue shaping surrounding matter. Planetary systems still orbit peacefully beneath stellar light. But the broader direction seems increasingly clear. Over extremely long timescales, usable energy differences diminish. The universe slowly smooths itself out. Some physicists describe photons as future carriers of entropy, because radiation becomes one of the dominant remaining forms of energy in the distant cosmos. As stars fade and matter grows colder, enormous seas of stretched low-energy photons continue drifting through expanding space. Not bright enough to illuminate worlds, not concentrated enough to drive complex activity, just thin backgrounds of ancient radiation crossing darkness, like fading echoes lingering after music ends. There is a quiet sadness hidden inside this future, but also a strange calmness. The universe does not appear headed toward violent destruction everywhere at once. Instead, Many cosmological models suggest an ending built from gradual exhaustion, a long cooling, a thinning of structure, a fading of energetic contrast. Sometimes this future is called the Big Freeze, not because everything suddenly becomes frozen in a dramatic instant, but because expansion and entropy slowly carry the cosmos toward thermal balance over unimaginable spans of time. Stars eventually consume their available fuel. Galaxies grow darker. The intervals between meaningful energetic events become longer and longer, and light itself stretches thinner across the growing void. You can almost imagine the future universe as an enormous winter landscape beneath an endless silent sky. Not dead in the ordinary sense, just quiet, extremely quiet. And perhaps one of the strangest aspects of all this is that photons themselves participate in the cooling without ever internally experiencing time. The timeless travellers continue crossing space-time exactly as light always does, while the universe surrounding them gradually transforms. A photon released in the distant future may still move locally at light speed, yet the cosmos through which it travels will become colder, emptier, and more diffuse with every passing era. The universe ages around the photon, not inside it. That distinction remains one of the deepest emotional threads running through this entire story, because it mirrors something strangely familiar about existence itself. Sometimes change arrives not because we internally become different overnight, but because the world surrounding us slowly shifts while we continue moving through it. Old neighbourhoods change, voices disappear, photographs fade. The background geometry of life quietly transforms around persistent memories. Redshift carries a similar emotional texture on cosmic scales. Ancient light continues travelling faithfully across the expanding universe, while the structure of space-time slowly stretches the message thinner and colder. And eventually, if expansion continues indefinitely, something even stranger begins to happen. The light does not necessarily disappear, but its information becomes harder and harder to recover. The wavelengths grow so enormous, the energy so diluted, that the message carried by the photons begins dissolving into near undetectable softness, like a voice becoming impossible to distinguish from distant wind. And this is where cosmology starts drifting gently beyond physics alone, towards something more reflective. Because the universe may not merely be cooling, it may slowly be becoming unreadable. The stars still shine for now, galaxies still fill the sky, ancient photons still arrive carrying recognizable patterns from the earlier cosmos, but expansion continues patiently beneath everything, stretching light, reducing contrast, softening energy, and somewhere unimaginably far ahead, only the faintest traces of the universe's once brilliant history may remain scattered across the dark. There is a difference between something existing and something still being understandable. An old photograph tucked inside a forgotten drawer may physically survive for generations. The paper remains. The image is still there in some faint form, and yet over time the faces begin to blur. Colours soften into pale shadows, names are forgotten. The moment the photograph once captured so clearly slowly drifts beyond recognition. The object survives, but the meaning fades. In many ways, cosmological redshift may be guiding the universe towards something similar. Throughout this journey, we have followed photons crossing immense distances through expanding space-time. We have watched wavelengths stretch, energies soften, and ancient light drift gradually toward colder and dimmer forms of radiation. But now another realization begins emerging quietly from the darkness. A photon can survive, while the information it carries slowly becomes impossible to recover. At first, this feels almost contradictory. If the light still exists, shouldn't the message survive too? Not necessarily, because information depends not only on existence, but on readability. Imagine hearing a familiar voice across a crowded room. At first, the words remain clear enough to understand. But as the distance grows and surrounding noise increases, individual sounds begin dissolving into static. Eventually, the voice still reaches your ears physically, yet no recognizable meaning remains. The signal survives. The message does not. Something similar may happen to light across cosmic timescales. As photons become increasingly redshifted, their wavelengths stretch farther and farther apart. Their energy spreads thinner across expanding spacetime. The radiation grows colder, softer, and more difficult to distinguish from the surrounding background of the universe itself. Eventually, some photons may become so stretched that recovering useful information from them becomes nearly impossible, not because the photons were destroyed, but because the differences carrying the message have faded beyond detection. This distinction matters deeply, because much of astronomy depends on contrast. Spectral fingerprints must remain distinguishable from surrounding noise. Temperature variations inside ancient radiation must remain measurable. Patterns hidden inside light must stay sharp enough for instruments to decode them. When those contrasts disappear, readability disappears too. The universe may continue containing ancient photons long after the stories they carried can no longer be reconstructed. There is something hauntingly beautiful about that possibility. The cosmos preserving traces of its history physically, while slowly erasing the ability to interpret them. Like libraries drifting through darkness after all languages have been forgotten, or radio transmissions crossing empty space long after the civilizations that created them vanished. The signals continue, meaning does not. This idea becomes especially powerful when we think about the cosmic microwave background. Right now, humanity can still detect the faint thermal afterglow of the early universe because its wavelengths remain within observable ranges for our instruments. But expansion never stops stretching that radiation. Over trillions of years, the wavelengths may become so enormous and dilute that future observers cannot realistically detect them at all. The background glow revealing the hot birth of the cosmos could eventually blend almost completely into undetectable cosmic softness. The evidence of the Big Bang would not necessarily vanish physically. It would fade informationally. And perhaps that phrase captures something profound not only about cosmology, but about existence itself. The universe appears to preserve many things partially while simultaneously making them harder to recover over time. Old starlight continues travelling. Ancient galaxies remain encoded into stretched photons. The past survives in fragments, yet expansion continuously increases the difficulty of reading those fragments clearly. Some physicists describe this process in terms of signal-to-noise ratio, the balance between meaningful structure and surrounding randomness. But emotionally, it may feel more like listening to music fade slowly into distant wind. The melody once existed clearly, then softly, then ambiguously, and finally only motion remains. No recognizable song, just drifting vibration. This gradual fading creates a strange inversion in the story of immortality. We often imagine immortality as permanent preservation, endless continuity, perfect survival through time. But photons suggest a subtler possibility. Something can endure physically while still losing practical significance. A stretched photon drifting across the far future universe may continue existing for unimaginable spans of time, yet its wavelength may become so enormous and diffuse that it can no longer meaningfully influence complex structures or reveal useful historical information. The photon survives, but the story it carried slowly disappears. And this realization changes the emotional tone of Redshift once again. Earlier, Redshift appeared almost beautiful. ancient light stretching gently across expanding space. Then it became historical, a way of reconstructing cosmic evolution. Later it became melancholic, galaxies drifting beyond visibility. Now it becomes something quieter still, a story about fading readability, the universe slowly outgrowing its own ability to remember itself clearly. There is a painful tenderness hidden inside that idea, because human life contains similar experiences everywhere. Voices in old recordings becoming harder to hear, languages disappearing across centuries, photographs surviving after identities are forgotten. Even memory inside the human mind behaves this way. Certain details remain vivid, while others soften into emotional outlines lacking sharp edges. Information fades gradually long before existence disappears completely. And perhaps this is why the night sky can sometimes feel emotionally overwhelming when viewed through cosmology. Every ancient photon arriving at Earth tonight has crossed unimaginable darkness, carrying fragile information across billions of years of expansion. The message survived, barely. Yet one day the universe may become so large and so diffuse that most of those ancient signals fade into practical silence forever. Future observers may inherit a cosmos stripped of visible history, a sky where evidence of expansion, cosmic origins, and ancient radiation has become unreadable, not because reality disappeared, but because space-time stretched the messages too far apart. And still, for now, the signals continue arriving. The stretched photons still carry recognizable fingerprints. The ancient radiation still whispers faintly through microwave detectors. The universe remains readable, at least for a little while longer. And that fragile readability may make our era of cosmic history far more unusual than we often realize. There is a curious possibility hidden inside modern cosmology. One day, the universe may become impossible to understand, not because intelligent life disappears, not because the laws of physics stop functioning, but because the evidence itself slowly fades beyond observation. At first, this sounds almost absurd. Science often feels cumulative. Knowledge grows from generation to generation. Telescopes improve, measurements sharpen. The future seems naturally destined to understand more than the past, and in many ways, that is true. But cosmology may contain a strange exception, because the universe itself is changing the visibility of its own history. Right now, when astronomers look outward into deep space, they can still observe billions of galaxies scattered across the observable cosmos. They can detect the faint microwave afterglow left behind by the early universe. They can measure redshift, trace expansion, and reconstruct cosmic evolution stretching back nearly 14 billion years. The universe still carries readable evidence of where it came from, but expansion continues, patiently, relentlessly. And over unimaginable spans of time, more and more of that evidence may slip away. The galaxies outside our local gravitational neighborhood are already drifting farther through accelerating space-time. Their ancient light still reaches us for now, but eventually those photons will become increasingly redshifted, stretched thinner and colder across the growing cosmic void. Future observers may watch distant galaxies dim gradually into invisibility, not exploding, not dying dramatically, simply fading beyond reach. One by one, the great galactic structures currently visible across the universe may disappear from future skies entirely. The cosmos will not necessarily become smaller, it will become lonelier. Imagine standing inside a vast library while thick fog slowly fills every room. At first, the shelves remain visible, titles can still be read, entire histories remain accessible, but little by little, the fog thickens. Distant shelves vanish first, their nearby sections blur. Eventually, only the smallest local corner remains visible at all. The book still exists somewhere in the darkness, but the library becomes unreadable. The future universe may evolve in a strangely similar way, and perhaps the most haunting example involves the cosmic microwave background itself. Right now, the ancient afterglow of the Big Bang surrounds us faintly in every direction. Sensitive instruments can still detect this primordial radiation because its wavelengths remain observable. But cosmological redshift continues stretching those wavelengths larger and larger over time. Trillions of years from now, the background radiation may become so diluted and stretched that no realistic detector could measure it effectively. The signal will blend into near-perfect stillness. The oldest visible evidence of the universe's fiery beginning may disappear from observation entirely. Future civilizations, if they exist, may never know the Big Bang happened at all. That realization carries extraordinary emotional weight, because it suggests that humanity may live during a rare and temporary window in cosmic history, a period when the universe remains young enough to reveal its origins. We often imagine ourselves arriving late in the story of the cosmos. After all, stars and galaxies existed for billions of years before Earth formed. Human civilization occupies only a tiny fraction of cosmic time, and yet, strangely enough, we may also have arrived unusually early enough that the universe still remembers itself clearly. The night sky we inherit today is extraordinarily rich with information. Redshifted galaxies reveal expansion. Ancient radiation reveals the young universe. Large-scale structures preserve traces of primordial fluctuations formed shortly after the Big Bang. The cosmos still contains visible memory, but memory requires accessibility, and accessibility changes with time. One day, future astronomers living deep in cosmic ages may observe only a single massive galaxy surrounding them. Perhaps the merged remains of what we now call the Milky Way and Andromeda. Beyond that local island of stars, the wider universe could appear dark and static. No detectable expansion, no visible galaxy clusters beyond the horizon, no measurable microwave background, no easy evidence for cosmic origins. From their perspective, the universe might seem eternal and unchanging, remarkably similar to how many humans once imagined the cosmos before the discovery of expansion. In a strange way, cosmological knowledge itself may be temporary, a brief achievement possible only during certain eras of universal evolution. There is something almost heartbreaking about that. The universe currently reveals itself through ancient photons that have not yet faded beyond detectability. Humanity exists during the fleeting interval when those stretched signals still remain readable enough for science to decode them. We are listening during the final moments before the library grows too quiet, and perhaps this transforms astronomy into something more fragile and precious than it first appears. The night sky is not an eternal archive permanently open for observation. It is a fading conversation, a temporary exchange between the present universe and the ancient light still crossing it. This realization has led some cosmologists to describe our era as a kind of golden age of cosmology. Not because humanity has solved every mystery, far from it, but because the observable evidence remains accessible in ways future ages may no longer inherit. Right now, galaxies are still visible, expansion is still measurable, primordial radiation is still detectable, cosmic history can still be reconstructed, the universe is still speaking clearly enough for us to hear it. There is a quiet gratitude hidden inside that fact, because every redshifted photon arriving tonight represents a message that survived extraordinary odds. Ancient light crossed expanding darkness for billions of years, and arrived during the brief era when conscious beings developed instruments capable of understanding it. That timing feels almost impossible. And yet here we are, small creatures standing beneath an evolving sky, learning to read the fading fingerprints of space-time itself. But even this remarkable readability cannot last forever. Expansion continues patiently beneath the stars. The cosmic archive grows colder. The visible universe shrinks toward isolation, and eventually, perhaps long after every familiar star has faded, only stretched radiation and immense darkness will remain drifting through the silence. Yet even then, the photons themselves may continue travelling onward, timeless, untouched internally, crossing an aging universe that slowly forgets how to interpret their light. If you sit beside a fireplace long enough late at night, eventually you notice the moment when the room changes. At first, the fire dominates everything. Warmth fills the air. Shadows dance softly against the walls. The crackling wood creates movement and life inside the darkness. But hour by hour the flames grow smaller. Bright orange fades toward deep red. The logs collapse inward quietly, and eventually only a few glowing embers remain beneath soft layers of ash. The room does not suddenly become cold all at once. It drifts there gently. Modern cosmology suggests the universe itself may follow a strangely similar path. Not toward a violent ending where everything explodes in a final catastrophe, but toward a long, slow fading. A gradual cooling stretched across spans of time so enormous that the human mind can barely hold them comfortably. This possible future is often called the Big Freeze. The name sounds dramatic, but the reality may be astonishingly quiet. The stars will not all vanish together. Galaxies will not disappear overnight. Instead, the cosmos may spend unimaginable ages slowly exhausting its remaining sources of concentrated energy. For now, stars continue burning through nuclear fusion. Deep within their cores, immense pressure forces atomic nuclei together, releasing light and heat into surrounding space. Our Sun performs this process every second, transforming tiny amounts of mass into radiant energy that warms Earth and allows life to exist. But stars are temporary. Even the longest-lived stars eventually consume their available fuel. Massive stars burn brightly and die quickly. Smaller stars glow more slowly and steadily, surviving for trillions of years in some cases. Yet given enough time, even these patient stellar embers fade. One day, star formation itself may largely cease. Galaxies currently contain enormous clouds of gas capable of forming future stars, but over immense timescales, much of this material will either become locked inside stellar remnants or drift too diffusely through expanding space to collapse efficiently again. The great era of star birth may eventually end, and after that, the cosmos enters a quieter age. Ancient stars cool gradually into dim remnants. Some become white dwarfs, dense stellar cores glowing faintly from leftover heat. Over even longer timescales, these objects may cool further into hypothetical black dwarfs. Cold, dark stellar ashes drifting invisibly through space. The phrase black dwarf sounds almost mythical, like something from a forgotten fantasy story. Yet it may describe one of the final stages of ordinary stellar evolution in the distant future universe. Cold remnants beneath dark skies. And surrounding all of this, the universe continues expanding, always stretching, always redshifting radiation farther toward lower energies. The night sky grows darker, not because light disappears completely, but because light becomes increasingly diluted across larger and larger distances. Photons continue travelling, but their wavelengths grow softer, longer, colder. You can imagine the future cosmos almost like an enormous winter plain beneath endless twilight. Vast stretches of darkness interrupted occasionally by fading embers of ancient stars. No dramatic collapse, no final explosion, only distance increasing, energy smoothing outward, and warmth becoming rarer with time. There is something deeply peaceful about this image once the initial sadness softens. The universe does not rage against its own aging. It simply unfolds. Even entropy, often described as a force of decay, can begin feeling less frightening when viewed through this slower cosmic perspective. Entropy is not necessarily destruction in the emotional sense. It is the gradual evening out of differences. A movement from sharp contrast toward equilibrium. Hot regions cool, bright things dim, intense structures soften. The cosmos slowly settles. And perhaps one of the strangest details of all is that photons may outlive almost everything else. Stars fade, galaxies isolate themselves across expanding spacetime. Complex activity becomes increasingly rare. Yet stretched low-energy radiation may continue drifting quietly through the universe for unimaginable durations. Timeless travelers crossing a cooling cosmos. In some distant future era, the universe may contain enormous oceans of faint radiation, spread thinly across expanding darkness. Not enough concentrated energy to illuminate worlds or sustain civilizations easily, but still present as gentle thermal backgrounds lingering after the great eras of cosmic structure have passed, like the final warmth remaining in stones after sunset, or the faint lingering scent of rain long after a storm has moved away. And through all of this, space-time itself continues evolving. Expansion does not pause simply because stars grow old. Galaxies beyond local gravitational groups drift permanently beyond visibility. The observable universe contracts towards smaller islands of remaining structure. The wider cosmos becomes increasingly unreachable. Future skies may appear astonishingly empty compared to the rich, star-filled universe humanity knows today. No bright rivers of distant galaxies crossing deep space. No visible cosmic web stretching across billions of light years. Only isolated remnants surrounded by immense darkness. Yet perhaps this future should not be imagined purely as tragic. There is also gentleness hidden inside it. The universe began in extraordinary heat and density, a place of turbulence, radiation, collision, and violent transformation. Over billions of years, expansion allowed complexity, chemistry, stars, planets, and eventually life to emerge. And after all those ages of activity, the cosmos may slowly return toward stillness again. Not identical to the beginning, but quieter, softer, less crowded with energetic contrast, almost like breathing outward after holding tension for a very long time. Sometimes when people first encounter the idea of the big freeze, they instinctively resist it emotionally. A cold, endless universe can sound frightening. But perhaps part of that fear comes from imagining cosmic timescales through the lens of human urgency. The universe is not rushing toward darkness tomorrow. The stars above Earth tonight will continue shining long after every human civilization now existing has transformed beyond recognition. The cosmos remains richly alive with structure and light for spans of time almost impossible to emotionally grasp. And even in the far future, photons continue crossing the dark. That detail matters, because while stars may fade and galaxies may separate, light itself persists with extraordinary patience. Ancient radiation survives, wavelengths stretch, energy softens. But the timeless travellers continue onward through the expanding sea of space-time, and this raises one final quiet question before our journey nears its end. If photons can survive across the death of stars, across the cooling of galaxies, across the fading of the visible universe itself, can light ever truly die at all? If you light a candle from another candle, Where exactly does the flame begin and end? At first, the answer seems obvious. One flame touches the wick, the second candle ignites, and now both burn separately. But if you watch carefully enough, the boundaries begin to feel less certain. Fire is not a solid object carried intact from one place to another. It is an ongoing process, a pattern sustained through continuous transformation. In some ways, light may be similar. Throughout this journey, we have spoken about photons as travellers crossing the universe for billions of years, and in many cases that picture works beautifully. Ancient radiation from distant galaxies really does continue moving through expanding space-time across immense cosmic distances. But once we look closely at how light actually interacts with matter, the story becomes stranger, and softer than the image of tiny immortal particles flying unchanged through emptiness. Photons interact constantly with the universe around them. A photon can strike an atom and disappear, transferring energy into the motion of electrons. Later, another photon may be emitted as the atom settles again. Light can scatter from dust drifting between stars. It can be absorbed inside molecules, reflected from planetary oceans, or redirected through clouds of gas surrounding newborn suns. At every stage, the boundaries of identity become difficult to define cleanly. Is the emitted photon truly the same photon that arrived earlier? Or has the original light ended, replaced by a newly created ripple carrying similar energy forward? Quantum physics does not answer this question in the way ordinary intuition expects. We naturally imagine objects persisting continuously through time. A stone remains the same stone. A river remains the same river even while water flows through it. Identity feels stable. But quantum processes often behave more like transitions than permanent objects moving intact from beginning to end. A photon absorbed into an atom no longer exists in its previous form. The atom itself temporarily changes state. Later, when energy is released again, a new photon emerges. The resulting light may resemble the original in some ways. But quantum mechanically, the continuity is subtler than everyday language suggests. This creates a deeply philosophical question hidden quietly inside ordinary starlight. What does it actually mean for light to survive? Perhaps the photon reaching your eye tonight is not the untouched ancient traveller we instinctively imagine, but part of a long chain of interactions unfolding across cosmic history. A ripple becoming another ripple, a pattern continuing through transformation rather than permanence. There is something strangely comforting about that possibility, because much of existence may work similarly. The atoms in your body were forged inside ancient stars, yet those stars no longer exist in the form they once did. Air enters your lungs and leaves again. Cells replace themselves continuously throughout life. Memory changes slightly each time it is recalled, and still, continuity somehow survives through change. Perhaps permanence was never about remaining untouched. Perhaps it was always about patterns enduring while details evolve. Light seems to whisper this idea everywhere. Even under extreme cosmic conditions, photons continue participating in transformation, rather than simple survival. Near powerful gravitational fields surrounding neutron stars or black holes, light can bend dramatically through curved space-time. In extraordinarily energetic environments, photons may interact in unusual ways difficult to observe directly under ordinary conditions. Sometimes, sufficiently energetic radiation can transform into matter itself. If a photon carries enough concentrated energy and encounters the right conditions, the energy may contribute to the creation of particle pairs, tiny bursts of matter and antimatter appearing briefly from radiation. Later, those particles may annihilate again, producing new photons, light becoming matter, matter becoming light. The boundaries blur. reality begins feeling less like separate categories and more like ongoing conversation between forms. And through all of this, the photon never experiences time internally in the ordinary sense. That paradox remains astonishing. The timeless traveller may participate in endless transformation without ever feeling duration the way conscious beings do. Ancient photons released near the beginning of cosmic history continue drifting across expanding space-time even while galaxies evolve, stars die, and the universe itself cools around them. And yet many photons also vanish constantly through interaction. Sunlight striking Earth does not remain untouched forever. It warms oceans, excites molecules, powers photosynthesis, reflects from snowfields, scatters through clouds. The original photons are absorbed and transformed into countless other processes. The universe is not filled with tiny immutable bullets preserving themselves unchanged eternally. It is filled with exchanges, conversions, transitions. And perhaps this makes the idea of photon death more complicated than it first appears. If a photon is absorbed, has it died? In one sense, yes. Its individual existence as that specific excitation has ended. But the energy continues, the field continues. New photons may emerge carrying related patterns onward, like one wave dissolving into the ocean while another rises nearby. The continuity belongs less to isolated objects, and more to the unfolding structure beneath them. This perspective changes the emotional meaning of immortality itself. Human beings often imagine immortality as rigid permanence, a fixed self continuing endlessly unchanged through time, but physics rarely presents reality that way. The cosmos appears far more fluid. Identity softens into process. Persistence emerges through transformation. Even the stars survive by changing. Even galaxies evolve continuously. Even light itself may persist not as frozen individuality, but as ongoing movement within deeper fields and relationships. And somehow, that version of continuity feels gentler, less anxious, more natural. Because the universe does not seem obsessed with preserving exact forms forever. Instead, it allows patterns to flow forward through endless variation. The ancient photons crossing the observable universe tonight may not remain perfectly identical to the instant they first emerge from primordial stars or hot plasma. But the larger story continues. The energy moves onward. The information survives for a while. The cosmic ripples keep travelling. And perhaps that is enough. Especially in a universe where even space-time itself evolves continuously beneath the journey. Which means the deepest truth about light may not be permanence, but participation. A vast, interconnected conversation, unfolding quietly across the dark. And if photons are less like immortal objects, and more like temporary waves moving through deeper fields, then perhaps the universe itself is built not from static things at all, but from patterns passing gently through one another. Late at night, when the wind moves gently through tall grass, it can sometimes create the illusion that the field itself is flowing like water. No single blade travels across the hillside. The grass remains rooted in place, and yet patterns move continuously through it. Waves pass from one region to another, shaping motion without requiring permanent objects to journey intact across the entire field. Perhaps the universe is more like that than we usually imagine. Human intuition naturally divides reality into separate things: stars, planets, stones, bodies, particles. We imagine the cosmos as a vast collection of objects drifting through empty space like pieces on a board game. But modern physics has slowly softened that picture. Again and again, a deeper investigation reveals relationships, fields, vibrations, and evolving patterns beneath the solid surfaces of ordinary experience. matter becomes mostly empty space held together by invisible interactions. Particles behave like excitations within underlying fields. Light acts simultaneously as wave and particle depending on how we observe it. Even space-time itself bends, stretches, and evolves dynamically, rather than remaining fixed and motionless. The closer science looks, the more permanence seems to dissolve into process. And perhaps nowhere is this transformation more emotionally visible than in the story of light. At the beginning of tonight's journey, we imagine photons as timeless travellers, crossing billions of years of expanding darkness. Ancient messengers carrying the memory of younger cosmic eras toward our telescopes and eyes. That image still holds truth. But now, after drifting through relativity, redshift, cosmic expansion, entropy, and quantum transformation, the image has softened. The photon no longer feels like a tiny glowing marble, racing unchanged across emptiness. Instead, light begins resembling something more fluid, a passing wave, a temporary structure moving through deeper fields beneath visible reality. There is something deeply calming about this shift in perspective, because permanence can be exhausting. Human beings spend so much of life trying to preserve fixed identities. We hold tightly to names, memories, appearances, routines, and versions of ourselves that feel stable. Yet time quietly reshapes everything around us. Bodies age, cities evolve, relationships drift, entire civilizations rise and disappear. The universe itself does not seem built from eternal stillness. It seems built from continuing transformation. And rather than resisting this, light simply participates. Photons stretch as space-time expands, wavelengths soften, energy disperses, ancient radiation cools into microwave whispers. Patterns evolve continuously, while still carrying traces of what came before. Even galaxies themselves behave like temporary structures within larger flows. Stars orbit quietly for billions of years, yet galaxies merge, distort, and transform through gravity over cosmic time. The night sky appears stable during a human lifetime only because human lifetimes are so brief compared to the rhythms of the cosmos. Reality moves slowly enough to disguise its own motion, but underneath, everything flows. Some interpretations of modern physics suggest that fields may be more fundamental than particles themselves. In this picture, the universe resembles an immense ocean of invisible structures extending everywhere through space-time. What we call particles are localized ripples, temporary disturbances moving through those fields. If so, then a photon may not truly be a standalone object at all. It may be more like a momentary pulse traveling through the electromagnetic field, a traveling pattern rather than an isolated thing. Like echoes moving through a cathedral long after the original sound was made, or wind crossing the surface of water at dusk. The waves appear real because the pattern persists long enough to observe, but the underlying medium continuously changes beneath it, and perhaps this helps explain why cosmology can feel strangely emotional when followed deeply enough. Because the universe revealed by modern physics is not cold mechanical machinery. It is dynamic, interconnected, layered with relationships stretching across unimaginable scales. Every photon arriving at Earth tonight carries evidence of interactions between space-time, quantum fields, gravity, thermodynamics, and cosmic history itself. The universe is not a collection of isolated events. It is a conversation. And redshift may be one of the clearest examples of this cosmic interconnectedness. A photon emitted billions of years ago cannot remain untouched because the universe surrounding it does not remain untouched. Expansion reshapes the wavelength, geometry alters the journey, entropy softens the energy, distance transforms the readability of the signal, The light changes because the cosmos changes. Nothing travels outside the universe's unfolding story. There is a quiet tenderness hidden inside that realization, because it means even the oldest surviving light remains connected to the ongoing evolution of reality. The photon is not separate from cosmic history. It participates in it continuously through relationship and transformation. And perhaps that idea extends beyond light itself. Human beings are also temporary patterns within larger processes. The atoms composing your body once drifted through ancient stars. The oxygen you breathe was forged in stellar furnaces billions of years ago. Every heartbeat depends on energy ultimately traced back to sunlight, itself generated by nuclear fusion deep inside a star born from older cosmic debris. You're not standing outside the universe observing it from afar. You're part of the same unfolding structure, a temporary arrangement of cosmic material becoming conscious enough to reflect upon its own origins. And for a brief moment in cosmic history, that awareness has learned to decode redshift, to study ancient photons, to reconstruct the evolution of space-time itself from stretched waves crossing the dark. There is something profoundly beautiful about that, not because humanity conquered the universe, but because the universe produced beings capable of listening to its oldest light. Even knowing that someday most of this visible history may fade beyond reach, even knowing that entropy continues smoothing differences towards stillness, even knowing that galaxies drift steadily beyond cosmic horizons, still, the waves continue, the fields continue, the timeless photons continue crossing the expanding dark. And now, after following them across nearly the entire visible history of the cosmos, we arrive quietly back at the question that began this journey. How can something timeless still seem to grow old? Perhaps the answer was never hidden inside the photon alone. Perhaps it was hidden in the changing universe surrounding the journey all along. Tonight, we began with a quiet paradox. A beam of light leaves a distant galaxy and crosses billions of years of cosmic history before arriving here. And yet, according to relativity, the photon itself may experience no passage of time at all. The timeless traveller. At first, the idea felt almost impossible to hold comfortably in the mind. How could something without an internal clock still arrive altered? How could light remain untouched by time, and yet become stretched, cooled, reddened, and weakened across the universe? Now, after drifting together through expanding space-time, ancient radiation, cosmic horizons, entropy, and fading information, the answer begins to feel softer. The photon does not grow old internally. The universe grows older around it. That small distinction changes the emotional meaning of everything we've explored tonight. Because redshift is not really the story of light becoming tired, it is the story of space-time changing during the journey. The cosmos itself slowly stretches every travelling wave moving through it. Wavelengths lengthen, frequencies soften, ancient radiation cools into quieter forms, information grows harder to recover. The visible universe drifts gradually toward isolation. And through all of it, the photons continue crossing the dark, timeless, silent, patient beyond imagination. There is something deeply moving about that persistence. Some of the light reaching Earth tonight began travelling long before mountains rose on this planet, long before human beings existed, long before mammals, forests, or oceans in their modern forms appeared beneath the sun. Ancient photons crossed expanding space while galaxies merged, stars exploded, civilizations emerged, and entire species vanished into history. The universe transformed completely around their journey, and still they arrived. Not unchanged, of course. Their wavelengths stretched, their energy softened, Their once brilliant radiation drifted slowly toward colder and dimmer forms, yet the ancient messages survived long enough for conscious beings to receive them. Perhaps that is one of the most extraordinary facts in all of science. Reality became capable of remembering itself, not perfectly, not forever, but for a while. Humanity exists during a remarkably narrow interval in cosmic history. The universe is old enough for stars, planets, chemistry, biology, and consciousness to emerge, yet still young enough that its earliest light remains detectable. We inherited a readable cosmos. The night sky above Earth is not merely beautiful, it is informative. Every red-shifted galaxy acts like a preserved memory drifting across space-time. Every spectral fingerprint carries traces of ancient chemistry. Every faint microwave photon from the early universe whispers about conditions near the beginning of cosmic history. The cosmos still speaks clearly enough for us to hear it, and perhaps that clarity is temporary. Far in the future, expansion may stretch most visible evidence beyond reach. Galaxies outside local cosmic neighborhoods may disappear into unreachable darkness. Ancient radiation may dilute into wavelengths too enormous and weak to detect. The wider universe could become silent to future observers, not because the cosmos ended, but because readability faded. The library remains. The lights simply grow too dim to read the shelves. There is sadness hidden inside that future, but also strange beauty, because impermanence gives meaning to observation. The fact that the universe remains visible now makes this era precious in a way that is easy to overlook during ordinary life. Human beings often feel small compared to cosmic scales, and in many ways we are. Yet small things can still witness immense truths. Tiny creatures standing on a thin rocky planet learn to measure redshift, to detect the thermal afterglow of the Big Bang, to trace the expansion of space-time itself using stretched photons crossing billions of light years. There is humility in that, but also wonder, and maybe even a quiet kind of belonging, because the atoms inside your body were shaped by the same cosmic processes we explored tonight. The oxygen you breathe, the calcium in your bones, the iron moving through your blood, all emerged from stellar histories carried forward through generations of stars. You're not separate from cosmic evolution. You're one of its temporary expressions, a pattern briefly capable of noticing the larger pattern surrounding it. And perhaps this is why the story of Redshift feels unexpectedly emotional once followed deeply enough. It begins as physics, wavelengths, expansion, relativity. But gradually it becomes a meditation on memory, transformation, impermanence, and the quiet fragility of meaning across time. The photon survives. The message fades. The universe stretches its own history thinner and thinner across the dark. And still, for now, the ancient light continues arriving. Even tonight, countless photons are entering Earth's atmosphere after journeys almost beyond comprehension. Some began travelling before the sun existed. Some carry traces of galaxies that may no longer resemble the forms we currently observe. Some are remnants of the early universe itself, stretched into faint microwave whispers by nearly 14 billion years of expansion. Timeless travellers still crossing the dark. And perhaps the deepest comfort hidden inside all of this is the realization that the universe does not seem afraid of change. Stars evolve, galaxies drift apart, radiation cools, structures fade, yet the cosmos continues unfolding with extraordinary patience, not rushing, not resisting, simply transforming, wave after wave, era after era. And somewhere inside that unfolding process, conscious life briefly opens its eyes and listens to the ancient light. Maybe that is enough. Maybe meaning was never about permanence. Maybe meaning lives inside the temporary ability to witness, to understand, and to feel connected to something larger than ourselves for even a small moment in time. Tonight, the universe remained readable. The photons still arrived. The cosmic story could still be heard. And somewhere far beyond the visible stars, ancient light continues drifting patiently through expanding spacetime, carrying the fading memory of a younger universe toward whatever distant futures still remain waiting in the dark. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey through light, time, and the quiet expansion of the cosmos. If you'd like to return for more gentle wanderings among the stars, you're always welcome here. For now, the ancient photons continue their endless crossing through the dark. And perhaps somewhere above you tonight, one of those timeless travelers is arriving softly at Earth after a journey older than memory itself. Sleep peacefully, wherever and whenever you may be.